Good day. Welcome to this video. In this video, I'm gonna show you how to code the I2C routine in the PIC18 microcontroller, specifically the PIC18 F45K22 microcontroller in assembly. And I'm gonna use information, about 90% of the information to code it is going to be obtained from directly from the data sheet. So to begin, I'm just going to show you quickly an overview of the code I'm going to use in this example to show you how the I2C routine operates in the specific code in this example. So I'm just going to open up the MPLAB code in this instance. Okay. Okay, this is the MPLAB code, the assembly code for the I2C routine. So just going to go through it from the top. Just zoom in. There. Right there. It's fine. So first off, the first thing to include is the title. Then the next line, the list. P equals to PIC18 F45K20. Include the P18 F45K22.inc file and include the configuration bits. And also this right after the configuration bits have been included. The C block is also there, and the C block contains these registers. Well, the C block is used to create custom registers. So imagine a C equivalent to this would probably be something like this: int I2C address, right? Will be initialized to 0, for instance, in C. So this would be like a C equivalent to this line of code here, which is I2C address. Int there. That's just an example, or char. So this is, in essence, is we're basically we're creating a variable called I2C address. I'm not going to explain the purpose of the variable just now. Just know this means an I2C. This means a variable in essence. So that's what the C block is for. So we have 5 variables here in this particular code: I2C address, I2C data, delay variable 1, delay var2, delay var3. Okay, that's this part. And here we have the org 0h go to init. This is the start of the code, and then the initialization of the code. This is the initialization. Here, so for the sake of this example, I've added these 3 lines, but they're actually not necessary in a physical implementation of I2C. I added these as a result of the nature of the simulation, because of the way I simulate this code. This particular code, I use a software called Proteus, and I need, apologies for that, and I need these 3 lines here, but they're not needed for the actual implementation, so you could just delete these when you need to apply these on hardware. And yeah, so this is the real initialization, the real part of the code. So first we initialize the oscillator, and we initialize the UART. Then the I2C is an I2C, yes, for the microcontroller is PIC18 microcontroller is initialized over here. And then for the oscillator, the speed is 4 MHz. For the UART, the baud rate is 19,200. That happens in initialization. I'm just doing a quick overview of the code, and then I'm gonna read and get the rest of the information from the datasheet. And also, you can also ignore these 2 lines. You ignore these 2 lines here, and ignore this line here. This is just specifically to simulate this code. The only one that matters is this guy here, and then the rest of it, and then the rest of the code matters. So it's in essence, this line with the comment, ignore this line, ignore these two lines. Okay. I'm not going to explain them just now, but they will be explained. It will make more sense as I go along. And so this line in essence calls a function where you're able to write 6 characters to an I2C device. In this case, the I2C device in this example is going to be an EEPROM. So you're going to be writing 6 characters to the EEPROM using this function right here. So this function, you're going to write 6 characters to the EEPROM using that function, and it's going to call that function. And after you write that, then there's another, right after that, there's another function called read I2C char, CHRARS. It actually means chars, like characters. So that function, we're basically going to read what you just wrote into the EEPROM, read that out to the terminal, enter. This is basically almost like pressing the enter key on your keyboard. So it goes to the next line. So there's a next line feature here, and then it reads those again. It reads those out to the terminal, and then enter again, reads what you just done to the terminal. Basically, this is what you just wrote into the EEPROM is going to be outputted on the terminal 3 times right after you do that, right after you write into it. So it's going to write it once, second time. Let's say you write for instance cheese into the EEPROM. It's going to output cheese on the terminal 1, 2, 3, 4 times. Yes, 4 times. So that in essence is what this code does. You type something into the terminal, 6 characters, and that's written to the EEPROM. And the EEPROM and the code reads all those 6 characters back out to the terminal. So basically it's sort of like an echo in this case, but this time you actually write into the EEPROM and reading from the EEPROM. Okay, so that in essence is what this code does. So now I'm just going to go to the data sheet, and in essence I'm going to go to the I2C section of the PIC18 F45K22 data sheet and go step by step, and how it explains exactly how to code the I2C routine. Okay, so the UART init, there's a different video for that. I'm not going to go through the initialization of the UART again. There's a different video for that. Probably gonna put a link for that down there, but there's a different video where I talked about extensively about the UART. You could just watch that. And apologies for my voice here. It's been a long day. I don't sound like this normally, so just bear with me. Okay, and now I'm just gonna go to the datasheet and explain from here, from the I2C init. Okay, let's just open up the datasheet over here. Okay, so to initialize the I2C, you have to go to the chapter 15 of the K22 PIC18 F45K22 datasheet, chapter 15, and you have to go to you have to scroll down here, look for right here I2C master mode, because to communicate with an EEPROM, the I2C is the in I2C communication, there's a master and a slave. In this case, the PIC18 is the master and EEPROM is the slave. So that's why we want to code the I2C routine in master mode. So you must click there, right there, and up here, right up here in section 15.6, I'm just zooming to that. It tells you right there how to initialize. It says master mode is enabled by setting and clearing the appropriate SSPXM bits in the SSPXCON1 register and setting the SSPXEN bit. Okay, And also here it says in master mode, the SCLX and SDAX lines are set as inputs and are manipulated by the MSSPX hardware. Well, this X here in particular, that means in this case we're using the MSSP1 module. So there are two modules for the master synchronous serial port. So we're using the MSSP1 in this example. This is going to be SSP1 CON1, the actual name of the register. And in this case, the SSPXM, I'm going to show you that just now. And by setting, and also here SSPXEN is going to be SSP1EN, right? And in master mode, and right here it says in master mode, the SCLX and SDAX lines are set as inputs. So that in essence is these SDAX and SCLX is found in the I2C register of the microcontroller. So to find that, you have to go into the .inc file, .inc P18 F45 K22.inc file. Okay, let me not bore you with that just now. It's in the SCL1 and SDA1 is in the I2C register. Just trust me on that. Okay, so let's go to SSP. As you can see down here, it shows all the registers of concern for the I2C, for coding the I2C. So here, register 15.3. And I'm just going to go there. And here, remember over there, it says to initialize, you must enable the SSP XEN bit. So this is bit number 5. And as you can see here, there are two modes. Well, the MSSP mode of the microcontroller can be operated in both SPI mode and I2C mode. In this case, we're using I2C mode. So down here, you see, so in SPI mode, we're not worried about that. I2C. So you see here in I2C mode, it says, by setting this bit to 1, it enables the serial port and configures the SDAX and SCLX pins as the source of the serial port pins. That in essence means we must BSF SSP1 CON 1, comma SSP1EN. In essence, I'm going to show you the code. I just want to get the words out first by the code. And the next one is next thing we have to do is we have to set it up in synchronous. We have to set up the MSSP module in I2C mode, right? In I2C master mode specifically. And as you can see down here, it says I2C master mode, and here it shows you a formula right here. A formula specifically for the speed of the I2C communication. So this register right here, which is SSP180D, determines the speed of the I2C communication to the EEPROM. So here, to initialize in master mode, in essence, set bit 3. Let me just zoom into that. We set bit 3, clear bit 2, clear bit 1, and clear bit 0. And that's exactly what we did in here. That's exactly what was done in code. Let me just open that up. Implement. Okay. So right here in the code, as you can see, first off, SSP1 CON register was cleared. And right here in the comments, it says mode is enabled by setting and clearing the appropriate SSPXM bits in the SSPX CON1 register. I just showed you that to do that, you have to set for I2C master mode according to those bit settings in the register of the PIC18 microcontroller datasheet. You have to set the SSP XM bit, which is bit number 3. So this is actually bit number 3 of that register, and it has to be set. And I just BCF'd bit 2, 1, and 0 just for fun. Okay, if this section bores you, I think you could just skip down to to the end, you just skip across the video. I don't think there are timestamps or anything. You just skip across the video where I'm doing the simulation, and you can have a go at the code. If you already know this section, just try to go to the section where I'm talking about the stuff you like. Anyway, so next, and by setting the SSPX bit, which is to enable the synchronous serial port. Okay, so BSF SSP1.1 SSP, and next, in master mode, the SCLX and SDAX lines are set as inputs. So that's this part here. tracy SCL1 SDA1, and just before, for all to use tracy, analog functionality must be disabled for port C, and that's done by doing this, which is moving literal bank D15 and clearing the unsol C registers to disable analog functionality of this port, which is port C. And for this particular one is to this is to SSP1ADD register is to initialize the baud rate of the I2C for I2C communication. So there's also a part in the datasheet I want to show you where it gives you that formula and talks about that. Okay, let me just go back to datasheet right there, and so it says baud rate, as you can see here in section 15.7, baud rate generator. So you click on there, and right there there's a formula called f-clock. So f-clock is the speed for I2C communication, and FOSC is the frequency of the oscillator, which in this instance is 4 megahertz, and SSPX-ADD is the register of interest. Now the register we're going to write to initialize the speed, and this is the formula. In the f-clock, there's a nice table underneath here if you're too lazy to calculate, which I am at this moment, too lazy to calculate right now. And here it shows you the FOSC, and so it says FOSC here 4 megahertz, which is what I set up in this example, and it says the value is going to be 9 right here, and it says the f-clock, the baud rate in this case, is going to be 100 kilohertz. So as you can see, there are other clock settings here. I mean, obviously you wanted 16 megahertz at 400 kilohertz, you would use that. You would also have a BRG value of 9 at 400 kilohertz. It all depends. You could either use this table, or you could, you know, go the long way route and just use this formula, plug in whatever speed you desire, and, you know, get the value for the SSPX-ADD. Yeah, but this is the formula we use for the SSPX-ADD register for the baud rate generator ready. Okay, so that's how 9 in the code was obtained. So that highlighted section there, which is 9. Yes, and as you can see, commented here are where the datasheet makes mention of these, just for that. Yeah, that's basically what the comments are. The comments are literally lifted directly from the datasheet. Right. Okay, and next I'm just going to show you the I2C write function and the I2C read function. So first, the I2C write, just go there in the datasheet. I'm just going to show you what it says in the datasheet first, and then the code afterwards. Because the reason I'm doing it that way is the code makes basically no sense if you don't understand, you know, the underlying theory. You believe the code more if the datasheet already told you that that's what you have to do to operate the I2C. Okay, so just go find it's at I2C master mode, enlarge that, and master mode. Okay, and just go there. So master mode operation. So what you want to look for is the typical transmit sequence right here. And in this case, I'm using I'm writing values into the EEPROM, and the EEPROM datasheet is here, right here. And I'll show you just now, you actually need the EEPROM as well. Information from the EEPROM and the datasheet. You need to use them together. I think that's what makes I2C a little bit complicated. It's unlike all the other modules. For instance, with the UART, you could just code the UART with information only from the datasheet, but for the I2C, you actually have to use the device you want to write to as well as the datasheet. So the first point here, it says the user generates the start condition by setting the SEN bit SSPX-CON2 register. So that's the first thing to do. That's the first step. And the second step is the SSPX-IF is set by hardware on completion of the start. Okay. I feel like I should show you these first two steps in the code before we move on. Okay. So first step, and let me show you so before we go into that, the EEPROM already gave us a way to write to it. So let me just scroll to the way the diagram is for a random byte. No, this is not it. A byte, right? Okay, yeah, this is the part where it talks about the byte, right? Okay, so in the byte, right, you can see here from this block diagram, it says the start bit first, the control byte, and you have to set the control byte, then acknowledge, then the word address, then acknowledge, then the data, acknowledge, and the stop bit right afterwards. And that's how you send data into the EEPROM. That's how you write to the EEPROM. So this control byte right here is essentially, it's almost like a device identifier. So for I2C, you won't always write to an EEPROM. Sometimes you might be writing to a camera, an ADC, a temperature sensor. It depends. There are lots of devices out there. An LCD module, an LCD display with an I2C interface. So you might be talking to that. So all of them have different control. It's almost like identifying, like, yes, I'm a camera, I'm an EEPROM, I'm an ADC, a temperature sensor. It just identifies those things. That's the control byte. And the word address is where you actually want to write to in whatever device it is, because these devices, well, let me just zone in on this case, because so this word address is basically the address you want to write to. So there are several registers in the EEPROM, and you want to write to a specific one at a given time. So that's where you have to tell the EEPROM the address, and the data is the actual data you want to write to it, right? And it's usually 8 bits. And in between sending all these, you have to clock out an acknowledge bit from the EEPROM. Basically, the EEPROM acknowledges that yes, I got the information you sent, and also the stop bit. So this is basically the blueprint for I2C writing. And now the data sheet. And okay, so let's talk about how exactly would you do that? We don't know how, so that's what we need the data sheet for. It's supposed to tell us in exactly how to code it, exactly what to do in the code to make each of these things happen, to write the control byte, to write the word address, to write the data. That's why we need the data sheet for that. We need so for example, to enable a start condition, we don't know how, right? And then the data sheet generates a start condition by setting the SEN bit of the SSPX-CON2 register, right? So it means we have to BSF this bit. And I'm just going to show that to you in the code. Okay, let me just do that. Okay, input app. There we go. This is the I2C, right? So first off, the user generates a start condition by setting the SEN bit of the SSPX.2 register. And that's what was done here. The SEN bit was set. And secondly, the next step, according to the datasheet, was the SSPXIF is set by hardware on completion of the start. SSPXIF is cleared by software. X in this case is 1, so SSP1IF. So how do we ensure? So it basically says here it's set by hardware on completion of the start. So basically what we do there is we poll it before we know we can move on. We poll this bit. We poll the SSP1IF bit of the PIR1 register. We poll that, so once it's set, we know that the start has been completed. So it's set by hardware on completion of the start. Keep in mind, in this case, hardware basically means the PIC microcontroller, so it's going to do that itself. So hardware basically means it's going to do that automatically, right? And after it does that, it's going to skip the next line, which is basically what this means is branch the previous lines. BRA $-2, which means literally branch the previous line. And so just imagine this is a label. This right here is a label for this line, right? So that's what that is, just in case it confuses you. I'll just put a quick comment there. Branch to the previous line. Okay. And once it's set, we're gonna have to skip this line, right? Once it's set, it means the start condition has been completed. And after that, SSP1IF must be cleared by software. So that's why we have to clear that bit of the PIR1 register. So fine, we're done with the start condition. Now let's go back to the EEPROM, datasheet. Apologies guys, this video is going to be long. I apologize in advance. It will be long because it's explanations. Okay, so this is the EEPROM datasheet. So next one is in the control byte. So control byte, we have to get that information. So what's the control byte is actually the device identifier for the EEPROM. So this is what it says here. This is the device identifier, the slave address in this case. So it's 1010XXX, which means don't care. And the last bit, it's 8 bits. And the last bit, this is basically going to be a 1 if we want to read from the device. And it's going to be a 0 if we're writing to it. So this is in essence the device identifier. Okay. Device addressing. Yeah, let's just go back to the write operation, and that's in essence the control byte. So let me just go back to the code there, and that's essentially what was done in the code. And before I show that to you, let me just go to and carry on the I2C routine transmit sequence. So after that, is cleared by software, the MSSP module will wait the required start time before any other operation takes place. Well, in this case, and from my past experience, no wait is required until the end. So this one, when you're coding it, take it with a pinch of salt. You can, I don't know, maybe you can delay there if you're really worried about I2C not writing it. You can put the delay there in the code, but from coding this in the past, I never added a delay there. So yeah, you can add one if you want. So 5, the user loads the SSPX buff with the slave address to transmit. The SSP1 buff is a register we use to send data to the I2C device, in this case the EEPROM. And how we do that is how the user loads the slave address to transmit. So the slave address in this case is the device identifier I talked about. So we literally just write a value into the SPX buff, and the address out to the SDAX pin until all 8 bits are transmitted. Transmission begins as soon as the SSP1 buff is written to, right? And after that's written to, and transmission has begun. So 7 says the MSSPX module shifts in the ACK bit, ACK stat bit of the SSP1 con2 register. So this is basically an acknowledge. This is what we acknowledge. This is the acknowledge part. Then after that, the MSSPX module generates an interrupt at the end of the 9th clock cycle by setting the SSPXIF bit. Right? I know this is not making a lot of sense. And then next, the user loads the SSPX buff with 8 bits of data. Again, and then the data is shifted out the SDAX pin until all 8 bits are transmitted. And the MSSPX module shifts in the ACK, another acknowledge. And that in essence is the end of I2C. According to the data sheet anyway. And then the end, the user generates a stop or restart condition by setting the PN or RACN bits of the SSP1 con2 registers. Okay, so let me just go back to the the EEPROM data sheet. So now this is where we are. We're about to send the control byte, and how is that done? Let's go back here. And that's done by just literally writing to the SSP1 buff register. So send the write control byte to the EEPROM, and that's how it's done. To send a byte to the EEPROM, you literally just write to the SSP1 buff register. And right after that, according to the datasheet, remember the datasheet of the EEPROM tells us we have to acknowledge after we send the write control byte, the control byte to the EEPROM, which is also the slave address, right? The write control byte to the EEPROM, which is the device identifier for an EEPROM, right? And it says we have to acknowledge right after that. Well, how do we do that? Basically, the datasheet tells us how to do that, which is the MSSPX module shifts in the ACK bit from the slave device address and writes its value into the ACK stat bit of the SSP1 con2 register. So for an acknowledge, this bit must be a 0. That's how we know the EEPROM has acknowledged that this value, a byte, has been received from the microcontroller by it. So that's how it acknowledges that. It acknowledges that by making this bit a 0, the ACK stat bit. So in essence, we have to pull that bit to ensure that it's a 0. So we do that. Bit test function, skip if clear. So if it's not cleared, we're going to go to the next line, branch the next line. If this ACK stat bit is not cleared, we're going to branch the next line. And this, we're going to go to this next line, and this line literally means branch to the previous line. And then we're going to be stuck on these 2 lines, in essence, until this guy becomes a 0. And once it's a 0, we're going to skip that. And right after that, the MSSP module generates an interrupt at the end of the 9th clock cycle by setting the SSP1IF bit. That in essence is what, remember, after an acknowledge, according to the datasheet, the MSSP module generates an interrupt at the end of the 9th clock cycle by setting the SSP1IF bit. Right. And in essence, that's what these 3 lines are for in the code. Literally, we're going to pull the SSP1IF bit until it's set. Right, so once it's set, we know that the 9th clock cycle has come and gone. So this 3 lines is essentially what the datasheet told us to do right after an acknowledge. Right, and then after the SSP1IF bit is set, we have to clear the SSP1IF bit because it says here it's cleared by software. according to the datasheet. And to clear the software, the code in essence is the software in this case. So clear that. And next, according to the datasheet, we have to send the word address. The word address is essentially the address we want to write to. We want to write to this address in the EEPROM, right? And let me just go back to the code. Okay. And to write to the EEPROM, the address, in essence, we literally move the address we want. Let's say we want to write to register 0 of the EEPROM. Literally move that into the SSP1 buff register. So here the user loads the SSP1 buff with the slave address to transmit, right? And that's that to the SSP1. And according to the datasheet, as soon as you write into the SSP1 buff register, the write sequence has already started. And after the write of the address has been done to the EEPROM, the MSSP module shifts in the ACK bit from the slave device and writes its value into the ACK stat bit of the SSPS contour register. In essence, that part is literally acknowledging, right? So after the word address, we have to do an acknowledge. So the PIC reads in an acknowledge bit from the EEPROM, acknowledgement bit from the EEPROM. So that bit should be a 0. The value of so to read in an acknowledge from the EEPROM, it's going to be written the value of whatever is read from the EEPROM, read out from the EEPROM for acknowledge is just a bit. That value has to be 0, and that value is going to be stored in the ACK stat bit of the SSP1 contour register. So we have to pull the ACK stat bit of the SSP1 contour register and make sure it's a 0 before we move on, to ensure that an acknowledgement has been received from the EEPROM. And that's what was done in the code here. And then implant. Okay. Let me just open code. Yes. And then in essence, it's these two lines here. Bit test function, skip if cleared, ACK stat, SSP1 contour. And if the bit isn't cleared, it means an acknowledgement has not been received. So it's gonna, this line, it's gonna keep branching to the previous line. So that's that. And then afterwards, the MSSP module generates an interrupt at the end of the 9th clock cycle by setting the SSPX IF bit. And yeah, and that's what was done here. The SSP1 IF bit of the PIR1 register, we're gonna poll it to ensure that we've indeed reached the 9th clock cycle, right? And as usual, after we find out it's been set, great, we're at the 9th clock cycle. Now we can clear that bit. In essence, this bit is to acknowledge that transmission has been completed. That's the official explanation for the existence of this bit. This bit becomes set by the hardware once transmission has been completed. So think of it as a way for us to know if transmission has been complete. You might be thinking the ACK stat is enough, but the ACK stat is actually an acknowledgement. It's an acknowledgement bit, acknowledgement from the EEPROM that it's been received, and this is for transmission. It's weird. According to the datasheet, this makes sense, because the datasheet says this, and therefore that's how it should be done. Okay. Okay, next up is the data. To write the data. The data is next. So after that acknowledge, now we write the data to the address, to the actual address that we want, and that's what the next 8 bits is. Okay, and to do that, in essence, just open MPLAB. Sorry, MPLAB. Okay. In essence, we just write the I2C data we want. Let's say we wanted to write a value of 2 into a particular register in the EEPROM. We write I2C data. This is a variable from the C block. I will create it in the C block. That was created in the C block. I'll move that into the SSP1 buff. And then right after that, according to the EEPROM datasheet, we have to wait for an acknowledgement from the EEPROM. And how that's done is it's the microcontroller reads an acknowledgement and stores its value in the ACK stat register. So if this ACK stat is 1, we have not received an acknowledgement. To receive an acknowledgement, this value has to be a 0, ACK stat. And then we do the same thing, we poll it until it's a 0, and then we'll move on. And then as we move on again, let me just show you that part in the way it talks about this in the datasheet. Which is right, yeah. As you see here, so address, see here, you look at point 10, it says data is shifted out the SDAX pin until all 8 bits are transmitted. Then afterwards, the MSSP puts in the ACK bit from the slave device and writes its value into the ACK stat bit of the SSP XCON2 register. And after this is done, usually after 8 bits are written in ACK and an acknowledgement is received, we usually as you can see here, steps 8 to 11 are repeated for all transmitted data bytes. We look at step 8, it says MSSP module generates an interrupt at the end of the 9th clock cycle by setting the SSP1IF bit. So we have to pull that bit after receiving an acknowledgement, after sending the data, right? Let me just go there. Okay. As you can see here, we have to pull for that bit again, right? We have to make sure that bit is 1 to ensure that transmission has been completed. Transmission of this 8 bits has been done. And then after, once that bit is set, then we know we could skip the next line and clear the SSP1IF bit of the PR1 register. And that's and right after that, the user generates a stop or restart condition by setting, well, this is directly gotten from the datasheet. So the user generates a stop or restart condition by setting the PN or RACN bit of the SSP XCON2 register. Well, now the PN bit is the stop bit, so we set that bit, right? And then interrupt is generated once the stop or restart condition is complete. So this is the interrupt. It's almost like for everything we transmit, this is one way to understand the purpose of the SSP1IF. For everything we send out of the PIC, anything byte or bit, we have to wait for transmission to be complete. We have to ensure it's completed. So this bit in essence tells us, great, whatever you wanted to be sent out has been sent out, you can carry on now. So if this bit never gets set, it's just stuck in this loop here, right? To just ensure that, you know, I2C COM goes smoothly. And then BCF, and then after that, after the bit is set, then we know transmission is complete. SSP1IF bit must be cleared by software, which is you coding, and it has to be cleared according to the datasheet, and that's why we always BCF PR1 SSP1IF. And that's that. And also for continuous write, it's important to add a delay. It helps for smooth functioning of the I2C for I2C writes. And in this particular case, in this code, all I'm going to do after this is literally going to show you a simulation showing that this works, that this particular code works. It's gonna work here without a delay, but in the hard way, it's best to add a delay there, I find. The individual that taught me how to do this, to do I2C, you know, gave me an advice to always put a delay there, and I find that it's always worked out. It's always worked out with a delay. I've never had issues coding I2C when I added the delay. Okay, so guys, that's in essence is how you do an I2C right. Start bit, wait for it to be sent by polling the SSP1IF bit, write the control byte, in essence a device identifier, to the EEPROM. This is the control byte, and also the control byte tells the EEPROM whether you want to write or read from it. In this case, we want to write to it, so the last bit is a 0. After writing, you have to wait for an acknowledgement according to the EEPROM datasheet. And how exactly we do that is told to us by the PIC18 datasheet. And then after that, for every data you transmit, bit or byte, you have to wait. You have to pull the SSP1IF bit to ensure it's been transmitted. And then next, we would send the word address to the EEPROM, and that's what this is. Send the word address to the EEPROM. The address we will actually want to write to EEPROM by writing into the SSP1 buff, and afterwards we have to acknowledge again. And after acknowledgement, we have to ensure that what we sent has been sent, right? And then right after that, we'd send the actual data by writing to the SSP1 buff and wait for an acknowledgement again, and then ensure it's been sent by polling the SSP1IF bit of the power 1 register. Okay. And as you can see, I broke it up into sections. So the start, so this is the start section, start bit, the writing the control byte section, and writing the address, right? That's the section for that. And next the actual data, and then the last section obviously is the stop, and then the last section, which is basically we need a delay there for continuous write, to continuously write to the EEPROM device. Okay, you could experiment and take out this delay and see how that works out. I have never tried that before, so you might want to see if you actually need this delay in the hardware. It would actually be interesting to see if you actually need this delay. I've never tried it without the delay, because I2C scares the living daylights out of me, so I never tried that. Okay, so that in essence is the I2C write. And now for the I2C read, we just go there to the EEPROM datasheet. If you're still listening, you're a champion. You will pass. You will be able to code this I2C properly. Okay, let me just go back to the PDF. Okay, I just go there. Okay, byte. Okay, so this is a random read. In essence, this is how the random read works. So you send a start, you enable start condition, and then next you send a write control byte, right? I know it's weird as a read, but the way the read works, in essence, you have to send a control byte first. You have to write to it the word address you want to read from, right? You have to do that first, and then write and then read out what you want from that address. So first you have to send a write control byte, then acknowledge, then you have to send you have to send the word address you want to read from, the address you want to read from, right? And then you acknowledge, and then you have to enable a restart condition, right? And then right after that, you send a control byte. Now you send a read control byte, right? Send a read control byte, and then acknowledge again, and then you actually gonna read out the data from the EEPROM. So after you read out the data from the send a acknowledge bit, a NAC for short, and then after that you send a stop condition, and then in essence is the I2C write. I2C read function from an EEPROM. And that's how you read from an EEPROM according to the EEPROM, right? And now let me look at the data sheet. So this is a typical receive sequence, and it's a bit, remember the exact way we read, we have to get from the EEPROM data sheet. It tells us exactly how you read, and in theory, the EEPROM tells us in theory how you read, but actually we have to get that info from the data sheet. So to start, we already know that basically you set the RACN bit. No, sorry, you set the SCN bit, but in this case I set the RACN bit because, like I said, I had some advice about how to code I2C in the past, and it's actually helpful to just use the RACN bit in this case. I'm going to show you that just now. And then after that, you set the control byte, just like in the write, in the I2C write function. You send the control byte through, so that all stays the same. The acknowledge, that part stays the same. The word address, sending out the word address, all that stays the same. And then you wait for an acknowledgement again, and then the restart, and then this is where things differ. So I'm gonna start to show you the code from here. Well, you could go through it and look at the differences. You could go through the code and look at the differences. If you look through this part, this early part again, it's essentially the same as in the write command. So I'm going to start explaining from here to be repetitive. Okay. And over here, just open the code now. Just in the read. As you can see in the read, the first part is essentially the same except this part here, which helps for continuous read. So the RACN bit is set this time instead of the SCN. I had some great advice in the past about that, and I find this works. Keep in mind, this way I've coded like this at I2C. It works very well, no problems. So that's why the RACN is set this time. Okay, so that part is essentially the same as the write function, I2C write. This part also the same, essentially sending the write control byte. This part sending the I2C address want to read from, waiting for the acknowledge, and waiting for transmission to be complete by polling the SSB1IF bit. That's essentially all the same as the write function. And then now this is where things differ. Okay, I made a mistake there. Let's just go through that. Okay, everything is fine now. Okay, yes, everything is back to normal. And this is where we have to start paying attention. So this is the restart, in a way. This is the restart, BSF, SSB1CON, the RACN. I remember for any bit you send out, any bit of byte you send out of the PIC, you always have to ensure it's been sent before you can carry on. And keep in mind, over here you could add a delay here, like a call, like I don't know, 10 millisecond delay to ensure what you sent has been sent. But this is risky. This part right here, that's actually risky. I don't advise you to do that. I think it's better to just pull the appropriate bit and ensure that it's actually been sent. You could put a delay there, but it could work, but it's risky. And you always have to, you must make sure you clear the SSB1IF by software. Make sure you clear that. And then now after that, we send to the read control byte. So this is the read control byte. We send that to the EEPROM. How do we do that? You just write this byte 1010, the next 3 bits are don't cares, and the last bit is a 1. That's a read control byte. You send that to the SSB1 buff register, and after that you have to acknowledge. You have to wait for an acknowledgement. So the MSSP module shifts in the ACK bit from the slave device and writes its value into the ACK stat bit of the SSPXCON2 register, and that's exactly what's done here. So in this next line, obviously it's branched to the previous line. So if the ACK stat bit is actually 1 instead of a 0, this loop is going to continue forever until this guy becomes 0. And if this becomes 0, it's going to skip that line, and it's going to ensure that it's been sent by, ensure that transmission has been complete, transmission of the read control byte, which in essence is what this bit does. It ensures that that has been completed. It becomes a 1 once transmission has been done, right? That's that. And then after that, this is where the read happens now. So to read, the user sets, this information is from the data sheet. So you could just check that out on the typical receive sequence for under I2C master mode in the data sheet. And the user sets the RCEN bit of the SSPXCON2 register, and the master clocks in a byte from the slave. So once we do that, once we set this bit of the RCEN bit of the SSP1CON2 register, we receive the master clocks in a byte from the address we've initially written to the EEPROM. So this address, right? Okay. Yeah. So clocked in that byte, and what happens after we send a byte or a bit to the EEPROM, the I2C device, must always wait for transfer to be complete. And after that's been completed, so the value we just received from the EEPROM is automatically in the SSP1 buff register. I know I might have confused you there a bit where I said we just transferred something, but keep in mind with the master, we always tell the slave what to do, right? In this case, the PIC is the master, and the EEPROM is the slave. That's just, well, that's not me saying that, okay? That's the data sheet. That's the actual name. That's the name it's called, the master and the slave. So the master always tells the slave what to do. And basically, in essence, when we set this, we're in essence telling the slave, right, okay, now I want to clock in the info from you. I want to clock in the data from that particular address that I asked for. So the master, in essence, is sending this bit. We're sending this to the slave, right? And for every time we send something to the slave, we have to wait for that information to be transmitted, if it's a bit or a byte, by doing this. So this particular bit will become a 1, will be set automatically by hardware once we've sent once what we've sent has been sent, right? Has been sent, transmission has been completed. Which in this case, after the 8th polling edge of the SCL, SSPXIF, and the bit are set, right? So, and after that has been set, we have to clear it. The master has to clear that bit. That bit has to be cleared by hardware, okay? And then after that, now we know that we've already clocked in the data we require. Okay. The thing is, the read is kind of confusing the first time, but after the second and the third time of looking through the code, it starts to make sense. Okay, so the SSP1 buff, so the information we wanted is now in the SSP1 buff, and then what we do is just write that to this variable, I2C data variable, right? This is just the data, this is just the register that's created by the user, by the code, to ensure that what we just received is nice and safe where we want it to be, which is an I2C data. So that's what this line does, moves them from the SSP1 buff to the I2C data register. And then after that, let me just show you this part quickly in the data sheet. Okay, and what's that? Data sheet. So you see now where we are is right here. We've already clocked the data we need. Now we'll have to send a NAC to the EEPROM and no acknowledge. Just, you know, this is basically like we don't want any more data, right? And now let me show you where it talks about that in the data sheet, the EEPROM data the microcontroller data sheet, exactly how to do it. Now we know how to do the acknowledge and how to read in the data. So let me just go down there. Okay, so you say here, it says the user sets the RCN bit of the SSPX-con register and master clocks in a byte from the slave. We've already done that. So after that, the master an ACK value sent to slave in ACK DT bit of the SSPX-con2 register and initiates the ACK by setting the ACK-EN bit. So in essence, there is an ACK DT bit in the SSP1X1Con2 register. In essence, that bit tells what is it? So we could send an acknowledge or a no acknowledge from the microcontroller to the microcontroller, which is the master, to the slave device. It could be we could send an acknowledge or no acknowledge. In this case, we want to send a NAC, right? But after we set that up, so that's what the ACK DT bit does, right? But that has to be clocked out. That has to be clocked out of the microcontroller. And that has to be sent out of the microcontroller. So the ACK-EN bit does that. So in essence, the ACK-EN bit sends out whatever the status of the ACK DT bit is. So after we clear or set this bit, we have to set this bit. We definitely have to set this bit for that information to be passed on to the slave device. So how do we do that? That's done by doing this. Let me just go back to the MPLAB code. Okay, over there. And that's done by, so in this case, to send a NAC, the ACK DT bit has to be set. So the master sets the ACK value sent to slave in the ACK DT bit of the SSP1Con2 register and initiates the ACK by setting the ACK-EN bit. As you can see, that's directly lifted from the data sheet. So here, when we set the bit, that's actually a NAC. When we set the ACK DT bit, it's actually a NAC. And to send that info to the slave, we have to set the ACK-EN bit. And after that's done, whatever bit you send out of the master, which is microcontroller, bit or byte, we have to wait for that to be sent out, which is essentially what we're doing here. SSP1IF. We always have to do that, bit or byte. And guys, you made it. That's the end of the I2C read. So you can give yourself a round of applause. That's in essence the I2C read. Just a quick recap. Our ACN send, well, this is actually supposed to be a ACN, but for continuous read, I had some great advice. It's better to do that, right? So that's the start. You send a start, then a write control byte. Wait for an acknowledge. Wait for an acknowledgement from the EEPROM, and then you wait for everything to be sent. Then after that, you write the address that you want to read from. Again, wait for an acknowledgement and wait for it to be sent. By wait for it to be sent, I mean wait for your data, what you wrote to the EEPROM, to be sent. Okay, to ensure transmission has been completed. Okay, and then next we do a restart condition, bit, wait for it to be sent. Alright, and then next, after restart condition, send the write control byte. Oh, sorry, read control byte. Do that. Wait for it to be sent. Great. So you wait, and then next is where we clock in the data from the slave. Clocking the data from the slave next. Okay, so this part was the read control. So after the read control byte, directly after that, we'll clock the data from the slave. And how we do that is to set the RCEN, and then we'll wait for that to be sent, and then we move whatever's in the SSP1 buff into the I2C data. And then right after that, we have to we have to send a no acknowledgement, and how that is done is literally set the ACK-DT bit of the SSP1 control register, and then we set the ACK-EN bit to send that through to the EEPROM, and then we'll wait, and that's the end of the I2C read. That's that. So now an overview of the actual code. So in the main function we're writing 4 characters. Sorry, 6 characters to the device. So if we look at the main function, first off, we're clear. We want to write to the 0 address, right? We want to write to the 0 to address 0 of the EEPROM first. So what we do, we call UART read. I explained this function in a UART video. I'm gonna link that. And you read, and then you write that. This is basically an echo to the terminal to just show you what you're typing, that you're not typing nonsense, right? Just automatically echo to the terminal. And then what that does is it moves whatever you just read, right? What has just been read by you, your user, it moves that into the I2C data. So that's what we're going to write into the EEPROM. So it moves that into this variable, and then it calls the I2C write function. And the I2C write function takes this as an argument. For those that, from your C++, remember that. And it takes this as an argument. It takes this as an input, in essence. It takes that as an input, and then it writes that out. Sorry, not writes that out, it writes that into the EEPROM into address 0 in this case. And then it increments the address variable. It increments the address variable because now you wanna write into address 1. And it basically does the same process again. Calls the UART read, reads whatever you type to it, echoes that out to you on the terminal, and then moves the data received to the I2C data register. Oh yeah, the comments here which explain each one, and then moves that into the data register to be written to the EEPROM to that specific location, right? And then it calls the I2C write function, increments the address. So now I want to write to address 2, and etc. It goes on and on like that for 6 addresses, and then it returns. Now after it returns from that all the way back to the top to the main, and after it returns, right? Remember I said ignore this particular line, right? It ignores that line, and yes. And after it does that, there's a function called read I2C characters. So in that read characters, what it does is it initializes address to address 0, reads, initializes to address 0, and then it calls a read function. Remember, all the read function is essentially all it needs is just to send it an address as an input. The read function needs an actual address as an input. So in this case, address 0. Then you call the read function, which we've already shown, and then after the read function, the output of the read function is essentially what we wanted. What was in address 0 of the EEPROM is going to be in I2C data, right? It's going to be in this I2C data register, and then that data register, we write that to the working register, and then we'll call the UART write function, so we can write that out to the terminal so we can see what was in that register. And then now we want to read from the next address, which is address 1. So we increment the I2C address variable, and then we go and then we read that from the EEPROM, and then whatever we read from the EEPROM is in this I2C data variable, move that to the working register and write that out to the terminal, right, to see what was in that address. And next time we increment again, and on and on and on like that for 6 addresses. And that in essence is what this particular code does. It writes to 6. It lets you write 6 6 characters into 6 different registers of the EEPROM, and it reads that out to you right away, 4 times specifically. So after it does that, it does an enter, next line, basically reads the 6 again, next line reads the 6 again. And remember these lines I told you guys to ignore. This in essence is for the code. So I'm simulating this project in Proteus, and Proteus does not allow to write and read, to write into an EEPROM and read from it right away. So I essentially made a push, what do you call it, a push, this particular push button where it's in port A. So this is port A0. It's connected to the port pin 0 of the port A register. And what it does is, if that register reads a 1 from the switch, from the input switch, then I can only write at that point in time. And if it's a 0, then I can only read. Okay, you could just ignore that, honestly. That's in essence is just so I can show you guys that this particular code is functional. So this right here and this, you could just go ahead and ignore those. It doesn't matter. Essentially what this code does is you write 6 characters in, and right away it's gonna read those and write those out to the terminal 6 times. That's what the code does. Okay, so guys, enjoy. Now I'm just gonna show you the functionality on Proteus. So I'm just gonna open Proteus now. Okay, so this is it. This is basically the, yeah. Okay, this is just a quick explanation of the schematic. So this right here is the virtual microcontroller. This is the EEPROM. These are the pull-up resistors for the SDA and SCL lines connected to the EEPROM. This is the virtual terminal, and this right here, this interface right here, is to reset the microcontroller. And this part right here, you actually don't need that. This part and this part right here are just for the simulation. That's all you need that for. And this actually is also not needed, so I'm just gonna delete that. And yeah, this essentially is the schematic, everything as it is, except this guy, which is only needed for the simulation. EEPROM, pull up resistors, virtual terminal, reset interface, and that's it. And when it opens up, the virtual terminal is going to open up in this case. It's taking a while. Yes, I wrote this already into the EEPROM, so now I'm going to write in another 6 characters into the EEPROM. So we're just going to close that, do that right there, open up. So I'm going to write A, B, C, D, E, F. This is an example, and that's an EEPROM. Now I'm going to close that, open that up, and we should find A, B, C, D, E, F. 6 characters read out of the EEPROM 4 times. I'm going to try one more. Do that, open up. This time I'm going to say cheese. Okay, it's been written to the EEPROM, and open up. Cheese, read out of the EEPROM, and that essentially is the code. Okay, function.